The universe is older than any mountain, older than any ocean, older than the Earth itself, and older than every star you can see with your eyes on a clear night. Its story reaches back about 13.8 billion years, to a time when space was hotter, denser, and stranger than anything we can truly picture. The Big Bang was not an explosion into empty space. It was the expansion of space itself. Every distant galaxy we observe carries a trace of that expansion, because the farther away a galaxy is, the more its light has been stretched on its long journey toward us. The universe has been expanding ever since its earliest moments. Even now, while planets turn and stars burn quietly in the dark, space itself is stretching on the larger scales. Galaxies are not simply flying through space from one central point. Instead, the distance between faraway galaxies grows because the fabric of space between them grows. The observable universe is much larger than 13.8 billion light-years across. Because space has expanded while light has been traveling, the most distant regions we can observe today are now about 46 billion light-years away in every direction. This means the observable universe is roughly 93 billion light-years wide. And yet, the observable universe may not be the whole universe. It is only the portion whose light has had time to reach us. Beyond that horizon, there may be much more universe, perhaps vastly more, stretching farther than we can ever see. The oldest light we can observe is not starlight. It is the cosmic microwave background, a faint afterglow from when the universe became transparent about 380,000 years after the Big Bang. Before that time, light could not travel freely because the universe was filled with a hot plasma of charged particles. Today, that ancient glow fills all directions of space. It has cooled to just a few degrees above absolute zero, and it appears as microwave radiation. It is like a soft fossil of the young universe, still surrounding us after nearly 14 billion years. In that early glow, scientists can see tiny differences in temperature. These small variations were the seeds of everything: large galaxies, galaxy clusters, cosmic filaments, and vast empty voids. The universe began almost smooth, but not perfectly smooth, and that slight imperfection made structure possible. Most of the matter in the universe is not the kind of matter that makes stars, planets, oceans, or bodies. Ordinary matter, the matter made of atoms, is only a small fraction of the total cosmic content. A larger share is dark matter, which does not shine or absorb light, but reveals itself through gravity. Dark matter helped shape the cosmic web. It gathered first, forming invisible scaffolding across space. Ordinary gas followed its gravity, collecting in dense regions where stars and galaxies could eventually form. There is also dark energy, an even deeper mystery. Dark energy appears to be causing the expansion of the universe to accelerate. It does not gather into galaxies like matter does. It seems to act on the largest scales, gently but persistently shaping the future of the cosmos. The universe is mostly dark energy and dark matter. The stars, planets, nebulae, and galaxies we see are made from only a small portion of what exists. In a strange way, the visible universe is the glowing surface of a much larger, invisible reality. The first atoms were mostly hydrogen and helium. Hydrogen is the simplest element, with one proton and one electron. It became the main fuel for stars. Helium, the second simplest element, was also formed in the early universe, along with tiny traces of lithium. The heavier elements came later. Carbon, oxygen, iron, silicon, gold, and many others were forged inside stars, in supernova explosions, and in extreme cosmic events such as neutron star mergers. The atoms in rocks, water, air, and living things were not all present in the beginning. They had to be made by the universe over time. Stars are cosmic furnaces. In their cores, they fuse lighter elements into heavier ones, releasing energy that becomes starlight. Every second, the sun converts millions of tons of mass into energy, and that energy takes the form of light and heat that eventually reaches Earth. The light from the sun takes about 8 minutes and 20 seconds to reach us. When sunlight touches your skin, it has just crossed about 150 million kilometers of space. The sun could vanish instantly, and Earth would continue receiving its light for more than 8 minutes before the darkness arrived. The sun is about 4.6 billion years old. It is not a young star, but it is not old enough to be near death either. It is roughly middle-aged, quietly fusing hydrogen into helium in its core. In about 5 billion years, the sun will become a red giant. It will swell enormously as its outer layers expand. Long before that distant stage, Earth's surface will no longer be the gentle world we know today. The sun is not especially large compared with many stars. Some stars are hundreds of times wider, others are much smaller and cooler. Red dwarfs, the smallest common stars, can burn so slowly that they may shine for trillions of years. No red dwarf has yet had time to die of old age, because the universe itself is not old enough. The smallest stars live so long that their full life cycles are still waiting in the future. The largest stars live the shortest lives. A massive blue star can burn through its fuel in only a few million years. Then it may explode as a supernova, scattering heavy elements into space and leaving behind a neutron star or black hole. A supernova can briefly shine as brightly as an entire galaxy. It is the death of one star, but also the beginning of new chemistry. From such explosions, gas clouds become enriched with elements that can later form planets. Neutron stars are among the densest objects in the universe. A spoonful of neutron star material would weigh billions of tons on Earth. These stars are the collapsed cores of massive stars, packed so tightly that atoms themselves are crushed. Some neutron stars spin rapidly and send beams of radiation into space. If those beams sweep across Earth, we detect them as pulses, and we call the objects pulsars. Some pulsars rotate many times per second with astonishing regularity. Black holes are regions where gravity is so strong that not even light can escape once it crosses the event horizon. The event horizon is not a solid surface. It is a boundary in space-time, a point beyond which escape becomes impossible. A black hole does not act like a cosmic vacuum cleaner from far away. If the sun were somehow replaced by a black hole of the same mass, Earth would continue orbiting almost as before, though without sunlight, life would not survive. The Milky Way has a supermassive black hole at its center. It is called Sagittarius, a star, and it contains about 4 million times the mass of the Sun. It lies about 26,000 light-years away from Earth, hidden behind dust and stars in the direction of the constellation Sagittarius. The Milky Way itself is a barred spiral galaxy. It has a central bar of stars and great spiral arms where gas, dust, and young stars are found. Our Sun sits in one of the smallest structures of the galaxy, far from the crowded center. The Milky Way is about 100,000 light-years across. Light needs around 100,000 years to cross from one side of the galactic disk to the other. The galaxy is so large that all of recorded human history is only a tiny moment compared with the time light takes to travel across it. The Sun orbits the center of the Milky Way. One full orbit takes roughly 225 to 250 million years. Since the Sun was born, it has circled the galaxy only about 20 times. The Milky Way contains hundreds of billions of stars. Around many of those stars there may be planets. The first confirmed planets outside our solar system were discovered only in recent decades, and now scientists know that exoplanets are common. Some planets orbit close to their stars, where heat is intense. Some orbit far away, where frozen darkness dominates. Some are gas giants, larger than Jupiter. Some are rocky worlds closer in size to Earth. there are planets that orbit two stars. From the surface of such a world, if it had a surface, the sky might contain two sunsets. These circumbinary planets show that planet formation can happen even in systems more complex than our own. There are also rogue planets wandering through space without a star. Some may have been thrown out of their solar systems by gravitational encounters. Others may have formed in isolation. They drift through the galaxy in darkness, warmed only by their own remaining internal heat. Jupiter is the largest planet in our solar system. It is so massive that it contains more than twice the mass of all the other planets combined. Its gravity has helped shape the history of the solar system, influencing asteroids, comets, and the formation of smaller bodies. Jupiter's Great Red Spot is a giant storm larger than Earth. It has lasted for centuries, though it has changed in size over time. The storm is a reminder that the gas giants are not still worlds, but restless atmospheres in motion. Saturn is famous for its rings, but it is not the only planet with rings. Jupiter, Uranus, and Neptune also have ring systems, though they are much fainter. Saturn's rings are made mostly of ice particles, ranging from tiny grains to larger chunks. The rings of Saturn are wide but very thin. They stretch for hundreds of thousands of kilometers, yet in many places they may be only tens of meters thick. From far away they look solid, but they are actually countless small pieces orbiting together. Uranus rotates on its side compared with the other planets. Its axis is tilted so dramatically that its seasons are extreme. For long periods, one pole can face the sun while the other remains in darkness. Neptune has the fastest winds measured in the solar system. Its atmosphere can produce winds faster than the speed of sound on Earth. Even so far from the Sun, Neptune is a world of motion and storms. Pluto is no longer classified as a major planet, but it remains a fascinating world. It has mountains made of water ice, plains of nitrogen ice, and a large moon called Charon. Pluto and Charon are so close in size that they behave almost like a double system. The asteroid belt lies between Mars and Jupiter. It is not a crowded field like in many movies. Space is still mostly empty there, with asteroids separated by vast distances. Ceres, the largest object in the asteroid belt, is classified as a dwarf planet. It is large enough to be rounded by its own gravity. It may contain a significant amount of water ice beneath its surface. Comets are ancient leftovers from the formation of the solar system. They are made of ice, dust, and rocky material. When a comet approaches the Sun, its ice can vaporize, creating a glowing coma and long tails that point away from the Sun. A comet's tail does not trail behind it like smoke behind a moving object. The tail is pushed by sunlight and the solar wind, so it generally points away from the Sun. This means a comet can travel tail first as it moves away from the inner solar system. The Moon is slowly moving away from Earth. Each year it drifts a few centimeters farther away. This happens because of tidal interactions between Earth and the Moon. The Moon helps stabilize Earth's axial tilt. Without it, Earth's tilt might vary more dramatically over long timescales, possibly changing the planet's climate patterns in extreme ways. Earth's tides are mostly caused by the Moon's gravity, with the Sun also playing a role. The oceans rise and fall because gravity stretches Earth slightly, creating tidal bulges as our planet rotates. Earth is not a perfect sphere. It is slightly flattened at the poles and slightly wider at the equator because of its rotation. This shape is called an oblate spheroid. Earth's atmosphere protects life from much of the Sun's harmful radiation. It also burns up many small meteoroids before they reach the ground. Every day, Earth collects dust and tiny particles from space. Most meteors you see in the sky are caused by small pieces of cosmic debris burning in the atmosphere. They are often no larger than grains of sand or small pebbles, yet they can create bright streaks of light. The stars you see at night are not all at the same distance. Some are only a few light years away. Others are hundreds or thousands of light years away. Constellations are patterns created from Earth's point of view, not actual groups of nearby stars in most cases. The nearest star system to the Sun is Alpha Centauri. It contains multiple stars, including Proxima Centauri, which is the closest known star to us. Proxima Centauri is a red dwarf, much smaller and dimmer than the Sun. A light year is a distance, not a time. It is the distance light travels in 1 year, about 946 trillion kilometers. Because space is so large, astronomers use light years to describe distances between stars and galaxies. When you look at stars, you are looking into the past. Sirius appears as it was about 8.6 years ago. Betelgeuse appears as it was hundreds of years ago. Distant galaxies appear as they were millions or billions of years ago. Betelgeuse is a red supergiant star in the constellation Orion. It is nearing the later stages of its life and will one day explode as a supernova. It may happen tomorrow in cosmic terms, or it may not happen for a very long time by human standards. The brightest star in the night sky is Sirius. It is actually a binary system, with a bright main star and a faint white dwarf companion. The companion, Sirius B, is the remnant of a star that once lived and died. White dwarfs are the remains of stars like the Sun. After such a star sheds its outer layers, the dense core remains behind. A white dwarf no longer fuses hydrogen in its core, but it can glow for billions of years as it slowly cools. One day, white dwarfs may cool into black dwarfs. But no black dwarfs are expected to exist yet, because the universe is not old enough for any white dwarf to have cooled that much. Space is not completely empty. Even in the space between stars, there are atoms, dust grains, radiation, magnetic fields, and cosmic rays. It is far emptier than the best vacuums on Earth, but it is not absolute nothingness. Interstellar dust may sound unimportant, but it shapes what we see. Dust can block visible light from stars and galaxies behind it. Infrared telescopes can see through some of that dust, revealing hidden regions where stars are forming. Nebulae are clouds of gas and dust in space. Some are stellar nurseries where new stars are born. Others are the remains of dead or dying stars. They can glow in beautiful colors because atoms in the gas emit light at specific wavelengths. The Orion Nebula is one of the nearest major star-forming regions to Earth. It is visible to the naked eye as a faint fuzzy patch in Orion's sword. Inside it, young stars are forming from collapsing clouds of gas. Stars form when dense regions of gas clouds collapse under gravity. As the gas falls inward, it heats up. If the center becomes hot and dense enough, nuclear fusion begins and a new star is born. Planets form from disks of gas and dust around young stars. Tiny grains collide and stick together, gradually becoming larger bodies. Over time, pebbles become rocks, rocks become planetesimals, and planetesimals can become planets. The solar system formed about 4.6 billion years ago from a rotating cloud of gas and dust. Most of the material became the Sun. The remaining material formed planets, moons, asteroids, comets, and smaller objects. The rocky planets formed closer to the Sun, where temperatures were high and ices could not easily survive. The gas and ice giants formed farther out, where colder conditions allowed ices to play a larger role in planet building. Earth's water may have come from multiple sources, including water-rich materials present during formation and later impacts from asteroids. The exact story is still studied, but Earth's oceans are part of a long cosmic history. Mars once had liquid water on its surface. Ancient river valleys, lake beds, minerals, and other evidence show that Mars was once warmer and wetter than it is today. Now its surface is cold, dry, and thinly covered by a fragile atmosphere. Venus is similar in size to Earth but very different in climate. Its thick carbon dioxide atmosphere creates an extreme greenhouse effect. Surface temperatures on Venus are hot enough to melt lead. Mercury is the closest planet to the Sun, but it is not the hottest. Venus is hotter because its thick atmosphere traps heat. Mercury has almost no atmosphere, so its surface temperatures vary dramatically between day and night. The largest moon in the solar system is Ganymede, which orbits Jupiter. It is even larger than the planet Mercury. Ganymede also has its own magnetic field, making it unique among moons. Europa, another moon of Jupiter, likely has a global ocean beneath its icy shell. That ocean may contain more water than all of Earth's oceans combined. Because of this, Europa is one of the most intriguing places to search for possible life beyond Earth. Enceladus, a moon of Saturn, sprays plumes of water vapor and ice from cracks near its south pole. These plumes come from a subsurface ocean. Spacecraft have flown through them and detected ingredients that make Enceladus especially interesting to scientists. Titan, Saturn's largest moon, has a thick atmosphere and lakes of liquid methane and ethane on its surface. It is the only moon known to have stable liquid lakes and seas on its surface, though they are not made of water. The Sun is one of hundreds of billions of stars in the Milky Way, and the Milky Way is one of perhaps trillions of galaxies in the observable universe. The scale is so large that every answer seems to open into another larger question. Galaxies come in many shapes. Some are spirals like the Milky Way. Some are elliptical, with older stars and less gas. Some are irregular, shaped by interactions, mergers, or turbulent histories. Galaxies can collide and merge. When they do, their stars usually do not collide directly because the distances between stars are so vast. But gas clouds can collide, compress, and trigger waves of new star formation. The Milky Way and Andromeda are moving toward each other. In several billion years, they are expected to merge into a larger galaxy. The night sky of the far future would look completely different. Andromeda is the nearest large spiral galaxy to the Milky Way. It is about 2.5 million light-years away. Its light began traveling toward us before modern humans existed. The cosmic web is the largest pattern in the universe. Galaxies gather along vast filaments and clusters, while enormous voids stretch between them. This web-like structure grew from tiny density differences in the early universe. Galaxy clusters are the largest gravitationally bound structures in the universe. They can contain hundreds or thousands of galaxies, along with hot gas and dark matter. The gas between galaxies and clusters can be so hot that it emits X-rays. The space between galaxies is not empty. It can contain thin gas, dark matter, radiation, and magnetic fields. In galaxy clusters, much of the ordinary matter is not inside stars, but in hot gas spread between galaxies. Some galaxies have active galactic nuclei, where supermassive black holes feed on surrounding material. As gas spirals inward, it heats up and releases enormous energy. These active centers can outshine all the stars in their host galaxies. Quasars are among the brightest active galactic nuclei. Some are visible across billions of light-years. They show us that supermassive black holes were already growing when the universe was young. Gravity can bend light. Massive objects such as galaxies and clusters warp space-time, causing light from objects behind them to curve. This effect is called gravitational lensing, and it can magnify distant galaxies that would otherwise be too faint to see. Einstein predicted that gravity bends light. In 1919, observations during a solar eclipse helped confirm that starlight passing near the sun was deflected. This helped make general relativity famous. Time is affected by gravity. Clocks run slightly slower in stronger gravitational fields. This effect is real and must be considered in technologies like GPS, where precise timing is essential. Time also changes with speed. According to special relativity, a moving clock runs slower relative to a stationary observer. These effects become noticeable at very high speeds, close to the speed of light. Nothing with mass can travel at the speed of light. Light in a vacuum travels at about 300,000 kilometers per second. and this speed acts like a cosmic limit in the known laws of physics. Because light has a limited speed, telescopes are time machines. The farther into space we look, the farther back in time we see. A deep image of the universe is also an image of cosmic history. The James Webb Space Telescope observes mainly in infrared light. This allows it to study very distant galaxies whose light has been stretched by cosmic expansion, and also regions hidden by dust where visible light cannot easily pass. The Hubble Space Telescope observes mostly visible and ultraviolet light with some infrared capability. Hubble changed our view of the universe by showing deep fields filled with galaxies, revealing that even tiny dark patches of sky contain thousands of distant worlds of stars. The sky is never truly empty. Even a small patch that looks black can contain countless galaxies if observed deeply enough. Darkness often means only that our eyes are not sensitive enough. The universe has no known center. From any galaxy, distant galaxies would appear to be moving away on large scales. This does not mean each galaxy is at the center. It means space itself is expanding everywhere. The Big Bang happened everywhere in the observable universe, not at one point in space. Every region we see today was once part of the hot, dense early state. The beginning is not in a direction, it is in the past. The universe may be flat on large scales, meaning its geometry is very close to the simple geometry we learn on ordinary surfaces extended into 3 dimensions. Measurements suggest that if the universe has curvature, it is very small across the observable region. The fate of the universe is still uncertain. If dark energy remains constant, the universe may expand forever, becoming colder and darker over immense timescales. Stars will fade, galaxies will grow isolated, and the night will deepen. This possible future is often called heat death or the Big Freeze. It is not a sudden ending, but a slow fading of usable energy. The universe would continue, but with fewer and fewer events of warmth and light. Another possible future, called the Big Rip, would occur only if dark energy grows stronger over time in a particular way. In that scenario, expansion could eventually tear apart galaxy clusters, galaxies, solar systems, and perhaps even matter itself. But the Big Rip is only a possibility, not a confirmed destiny. The universe may also contain things we have not yet imagined. Every generation has discovered that reality is larger and stranger than expected. The night sky looks calm, but behind it are expanding space, invisible matter, ancient radiation, black holes, dying stars, and newborn worlds. There are more stars in the observable universe than grains of sand on Earth's beaches, though such comparisons are estimates. The number of stars is so vast that it becomes almost impossible to hold in the mind. Yet each star is a physical object, with mass, temperature, history, and light. Some stars are born alone, but many are born with companions. Binary and multiple star systems are common. The Sun is somewhat unusual in being a single star without a stellar companion. The color of a star tells us about its temperature. Blue stars are hotter, red stars are cooler. The Sun appears white from space, though Earth's atmosphere can make it look yellow or orange, especially near sunrise and sunset. Stars twinkle because Earth's atmosphere distorts their light. Planets usually twinkle less because they appear as tiny disks rather than points. Above the atmosphere, stars shine more steadily. The International Space Station orbits Earth about every 90 minutes. Astronauts aboard it can see many sunrises and sunsets in a single day. It is close to Earth compared with the Moon, but it still moves through the edge of space at great speed. Earth's magnetic field helps protect the planet from charged particles from the Sun. When those particles interact with Earth's atmosphere near the poles, they can create auroras, curtains of green, red, and purple light. Auroras also occur on other planets. Jupiter and Saturn have powerful auroras shaped by their magnetic fields and interactions with charged particles. The universe repeats patterns, but each world gives them its own form. The Sun has an atmosphere too. Its outer atmosphere, the corona, is extremely hot, reaching millions of degrees. During a total solar eclipse, the corona can be seen as a pale glowing halo around the darkened Sun. Solar flares and coronal mass ejections can send bursts of energy and charged particles into space. When they reach Earth, they can affect satellites, power systems, radio communication, and auroras. The Sun loses mass over time through radiation and the solar wind. It is still overwhelmingly massive compared with Earth, but it is slowly changing, as all stars do. Every atom in your body has a cosmic history. The hydrogen in you may come from the early universe itself. The carbon and oxygen were made in stars. The heavier elements were shaped by stellar deaths and cosmic collisions. You are made of ordinary matter, but that ordinary matter has crossed deep time. It has been gas, dust, star material, planet material, ocean chemistry, and living tissue. The universe does not simply surround us, it continues through us. The night sky is a record of motion. Stars move through the galaxy, galaxies move through the cosmic web, and the universe expands on the largest scales. Nothing is perfectly still. Even the Milky Way is moving. It travels with the local group and is influenced by nearby large-scale structures. Our galaxy is part of a cosmic flow much larger than itself. The local group contains the Milky Way, Andromeda, Triangulum, and many smaller galaxies. These galaxies are gravitationally bound together. While the wider universe expands, the local group remains held by gravity. Not all galaxies are moving away from us. Andromeda is approaching because local gravity overcomes cosmic expansion at this scale. Expansion dominates over enormous distances, but gravity still rules within bound systems. There are places in the universe called voids where galaxies are much rarer. These voids can span enormous distances. They are not completely empty, but compared with filaments and clusters, they are quiet regions of space. Some of the oldest stars in the Milky Way are found in globular clusters. These are dense, spherical groups of ancient stars orbiting the galaxy. They can contain hundreds of thousands or even millions of stars. Globular clusters are like fossils from the early history of galaxies. Their stars are often very old and poor in heavy elements compared with younger stars like the Sun. The age of a star can be estimated by its color, brightness, composition, and position in stellar evolution models. Stars are not all alike. They are clocks, furnaces, and records of the chemical history of the universe. The universe is filled with neutrinos. These tiny particles are produced in nuclear reactions, supernovae, and the early universe. Trillions of neutrinos pass through your body every second, almost always without interacting. Cosmic rays are high-energy particles from space. Some come from the Sun, others from supernovae, and some from even more extreme sources. When they strike Earth's atmosphere, they can create showers of secondary particles. The vacuum of space can still contain virtual particles, fields, radiation, and quantum activity. Empty space is not as simple as ordinary emptiness. At the deepest level, even nothing seems to have structure. Quantum physics rules the tiny scales of matter and energy. General relativity rules gravity and the large-scale structure of space-time. Scientists still seek a complete theory that unites these views, especially for places like black holes and the earliest universe. Black holes may slowly lose energy through a process known as Hawking radiation. For large black holes, this effect is extremely tiny. A stellar or supermassive black hole would take far longer than the current age of the universe to evaporate. The universe has produced beauty without needing to know it is beautiful. Spiral galaxies, glowing nebulae, icy moons, quiet planets, and ancient light all arise from physical laws. The mystery is not lessened by understanding, it often becomes deeper. The farther we look, the younger the universe appears. A galaxy seen 12 billion light-years away is not being seen as it is today, but as it was when its light began traveling. That galaxy may now be completely different, changed by time, mergers, star formation, and expansion. Some of the galaxies Webb observes are so distant that their light has been stretched into infrared wavelengths. By studying that stretched light, astronomers learn about early galaxies and the conditions of the young universe. A galaxy's redshift tells us how much its light has been stretched by cosmic expansion. Higher redshift generally means we are looking farther back in time. Redshift is one of the key tools for mapping cosmic history. The early universe had a period called the Cosmic Dark Ages. After the first atoms formed and before the first stars ignited, there was no starlight. Hydrogen and helium drifted through expanding space while gravity quietly gathered matter into the first structures. The first stars were likely very different from many stars today. They formed from almost pure hydrogen and helium before heavy elements had enriched the universe. They may have been massive, bright, and short-lived. When the first stars died, they began the chemical enrichment of the universe. Their explosions scattered heavier elements into space. Later stars and planets formed from this enriched material. The first galaxies were probably small, irregular, and turbulent. Over time, they merged and grew into larger galaxies. The grand spirals and giant ellipticals of the modern universe are products of billions of years of assembly. Galaxies can stop forming stars when they lose or heat their cold gas. Without cold gas, new stars cannot easily form. Such galaxies become quieter and redder as their young blue stars fade. The universe has a history of star formation. It formed stars most rapidly billions of years ago, during a period sometimes called cosmic noon. Since then, the overall rate of star formation has declined. Even now, new stars are still forming. In the Milky Way, cold clouds collapse into young stars. The galaxy is old, but it is not finished. The Earth is about 4.4 billion years old. It formed from material orbiting the young Sun. Over time, it differentiated into layers, with heavy materials sinking inward and lighter materials rising. Earth's core is mostly iron and nickel. Its outer core is liquid, and its motion helps generate Earth's magnetic field. Deep beneath our feet, the planet is still active. Volcanoes, plate tectonics, erosion, and impacts have shaped Earth's surface. Unlike many airless worlds, Earth constantly renews itself. Its surface is not a frozen record, but a changing story. The Moon preserves ancient impact history more clearly than Earth because it lacks weather, oceans, and plate tectonics. Craters can remain for billions of years. The Moon is like a quiet archive of early solar system impacts. Meteorites on Earth can be older than the planet's surface rocks. Some contain material from the earliest solar system. By studying them, scientists learn about the conditions before planets fully formed. Some meteorites contain tiny grains older than the Sun. These pre-solar grains formed around ancient stars and survived the birth of the solar system. They are microscopic messengers from stars that died before our Sun was born. The universe is not silent in every sense. Space has no air to carry ordinary sound, but cosmic events can create waves in plasma, vibrations in stars, and gravitational waves in space-time itself. Gravitational waves are ripples in space-time caused by accelerating massive objects, such as merging black holes or neutron stars. They were directly detected for the first time in 2015. Their discovery opened a new way of observing the universe. When two neutron stars merge, they can create heavy elements like gold and platinum. Such events also produce gravitational waves and light, allowing astronomers to study them in more than one way. The gold on Earth may have come from ancient cosmic collisions. Long before humans shaped it into rings, coins, or instruments, it was made in extreme astrophysical events and scattered into space. Every peaceful night, sky contains violent histories. Stars have exploded, galaxies have collided, black holes have merged. Yet from Earth, the sky can appear calm because distance softens the drama into silence. The universe is full of scales beyond ordinary experience. Atoms are tiny. Planets are enormous compared with people. Stars are enormous compared with planets. Galaxies are enormous compared with stars. The observable universe is enormous compared with galaxies. And still, the laws of physics connect these scales. The same gravity that holds the moon near Earth also shapes galaxy clusters. The same atoms made in stars can become dust, oceans, air, and life. The universe is not only a place of objects, it is a place of relationships. Planets orbit stars. Stars orbit galaxies. Galaxies gather in groups and clusters. Clusters trace the cosmic web. Light connects distant times to the present. A telescope is a way of receiving old messages. It does not pull the universe closer. It collects the light that has already crossed space. Astronomy is the art of listening to ancient light. The more we learn, the more the universe seems both understandable and mysterious. We know the age of the universe with remarkable precision, yet we do not know what dark matter is. We can map billions of galaxies, yet we do not know the full nature of dark energy. There may be planets in the galaxy with oceans beneath ice, planets with skies of unfamiliar colors, planets with no stars, planets with 2 suns, planets covered in lava, planets frozen in darkness, and planets that no telescope has yet seen. Somewhere, stars are being born right now. Somewhere, a supernova remnant is spreading heavy elements into space. Somewhere, a planet is forming from dust. Somewhere, a black hole is quietly bending light. Somewhere, ancient photons are arriving after traveling for billions of years. And here, under one small sky, we can think about all of it. The universe is vast, but it is not separate from us. Its history is written in the atoms of Earth, in the light of the sun, in the tides raised by the moon, and in the quiet darkness between the stars. Every night, the sky offers the same gentle reminder. We're living on a small planet beside an ordinary star, inside a vast galaxy, within an expanding universe that began in fire, grew through darkness, awakened in starlight, and is still unfolding. The universe is ancient. The universe is changing. The universe is mostly unseen. And yet, in the calm darkness above us, it still gives away its secrets, one faint light at a time.